Okay, so 4.6 related rates. So related rates are really similar to optimization problems. The only difference, the big difference, is going to be you're not technically optimizing. You're not, taking the max or the min. And then let me show you a couple problems, okay? So related rates, you're really relating different derivatives with each other, okay? Different rates. So there are these steps. I'm not going to go through each step, but basically I'm going to show you a couple problems and see how it works out, all right? First of all, you do need some formulas. So the big thing is you have to draw a picture, and then in that picture you have a bunch of information. You got to figure out, okay, what formula am I using? What's the big, is it like area equals pi r squared, circumference equals 2 pi r? I mean, what is it that I'm really doing here, okay? So the first one is a ladder problem. So this I call a ladder problem, but because it's always about a ladder, like a ladder leaning on a house or whatever. But any right triangle is going to use a squared plus b squared equals c squared, right? This is very specific because a ladder is fixed. So you'll see what I mean. Okay. So let's say you have, a lot of information, but you're going to draw a picture to go with it, because that's the very first thing we do. We draw a picture, and then we label the picture, and then we see what we need to do after that. So a ladder that's 10 feet long, so imagine this ladder, is leaning against the side of a building. So there's a ladder leaning against the side of a building. We're going to go ahead and draw that, okay? So the ladder is 10 feet long. And then it gives you this other information, and let's see where that goes in our picture. Okay, so we have the side of a building, we have the ground, which make a 90-degree angle, because that's what buildings and grounds do normally. And then you have a ladder leaning against the side of the building. Well, the ladder is 10 feet long. So there's my, if this is a squared plus b squared equals c squared, there is my hypotenuse, which is c, right? So c equals 10. And then we'll kind of ignore everything else for a second. So c equals 10. And then it says the ladder is moving away from the building at a rate of 1/2 feet per second. So the ladder is moving this way. So this is coming down and this is going that way, right? So this part is moving away from the building, and that is a rate. So how do I know that it's a rate? I know it's a rate because it says feet per second. So 1/2 feet per second means instead of the value of A or B, I mean, I labeled it however I wanted, but I said this was A, B, and C. So I said instead of A, this is actually A prime. So I wrote it like this so you can really see that this is a rate in terms of time. So it's a derivative of A in terms of T, because it's in terms of seconds, which is a time unit, okay? So really this is dA over dt, and then you can write it as A prime if you want, okay? So that equals 12, or that equals, sorry, 1/2. So I have my 10, I have my 1/2. And it says find the rate at which the ladder is falling down the building. Okay, I'm finding another rate. I'm finding this rate, the rate at which this is falling. So I'm really finding B prime or dB over dt, okay? And then when the ladder is 6 feet away. So when the ladder is 6 feet away, well, that's not this, it's going to be this part. So then they're telling you that's 6. Okay, so here's what we have. We have the 10, the 6, the 1/2, and the question mark. So how did we find the 8 right here? Well, if this is a 6 and this is a 10, you can use a squared plus b squared equals c squared. You also can realize this is a 3, 4, 5 triangle. So this is 3 times 2, 4 times 2, and 5 times 2. So that must be an 8. Okay, so a lot of times we're using 3, 4, 5 triangles. We're using 5, 12, 13 triangles. Those are the two most popular ones that I'm going to use over and over again because those show up a lot. Okay, and they make our numbers nice and easy to deal with, right? So 5, 12, 13 is a Pythagorean triple, and then 3, 4, 5. Okay, how do we get that 0? Well, c prime, or dc over dt, the derivative of c in terms of time, is going to be the rate that this ladder is changing as it moves. Well, the ladder's not changing. The ladder's staying the same. So that's why c prime is 0. Okay, so I have all of my variables plugged in. Okay, a right triangle I can relate with a squared plus b squared equals c squared. And then I take the derivative and I do it implicitly. So the 2 comes forward, I get 2a prime, or I can write it as dA over dt. Either way is okay. The only reason I wrote it this way is for you to really see that you can't just leave it. You can't be like, oh, this is just 2a when I take the derivative. No, 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 no. This is not in terms of a. This is not in terms of b. This is not in terms of c. This, all the rates are in terms of time. So that's why it's derivative of a in terms of time, derivative of b in terms of time. So that's why it's a prime, and then here we have 2b prime equals 2c prime. And then I divided the 2's away, and then I just plug in what I have over here. So I plug it all in, and I solve for b prime. Okay, think about the fact that's negative. Why would that be negative? So how come that rate would be negative? Well, it's because the ladder is falling down this way. As the ladder goes out this way, it must be falling down this way. So that b is getting shorter. At b equals 8, it's right there. It's getting, like, the rate of it is changing at this speed, and it's getting shorter, okay? But then we have to answer the question, because that's the last part here. It says, answer the question. So the question is, find the rate at which the ladder is falling down. What rate is the ladder falling down? The ladder is falling down at this positive rate. And you have to write the whole thing. So 3/8 feet per second. How do I know it's feet? Because, you know, b is in feet. How do I know it's per second? Because that is my per time, right? Per second right here. I have that in the original. So feet per second. That's a positive rate. It's falling down at a positive rate. Okay? Okay, so let's try the other one. So this is our second one. This is very, very popular as well. So it is the cone problem, okay? We're going to call this AP's second favorite. If a cone is, so the first thing is, I mean, if you look at this cone, ignore all the writing, okay? If you look at this cone, basically, if you have a cone, a lot of times what's happening is there's like water that's coming out, or there's sand that's getting filled in. So if you imagine this as a substance and you're filling it with something, it just like expands inside the cone, or it gets smaller inside the cone. But what happens is the big cone and the little cone that's getting filled up, right? Whatever's filled up in the cone, those are similar figures. So everything's proportional. So what this says is that the radius and the height here for the actual cone versus the radius and height here. So here's another radius, here's another height of the little part of the cone. Those are going to be proportional. Whatever, like r over r equals h over h, basically, okay? So we say these are proportional. We can say that this equals a number over a number, and then we can solve for r or solve for h later so that we don't have two variables. We only end up with one variable for some situation like this, where something's getting filled or, you know, emptied or whatever, okay? So let's say in this problem, water is draining. So this is water. It's coming out of a conical reservoir 20 feet in diameter. So right away, if it's 20 feet in diameter, we can say this r equals 10, right? And then it's 50 feet deep. Okay, so this is 50 feet deep. We're going to call that h. So the height is 50. And the water is draining at a rate of 12 feet cubed per minute. So if water is draining at that rate, okay, this is a derivative. What kind of derivative? I know it's a derivative because it says feet cubed per minute. And then I know it is a volume derivative because it says feet cubed. So 12 feet cubed per minute is a rate for volume. So actually v prime equals negative 12. Why is it negative 12? Because that's the water is draining at that rate. So really water's coming out at that rate. So the volume is changing and it's getting smaller. Negative 12 feet cubed per minute. Okay. And then it says, how fast is the water level falling? Okay, so this is the water level. How fast is that falling? How fast is a rate. You're looking for basically h prime. So this little h over here, because this is the big H, and there's a little h, right? So how fast is this little h falling? So that's h prime. When the little h is 20, when the depth of the water is 20 feet. Okay, so I have all my information here. And then I think about, okay, well, I have like V prime, so I probably need volume of a cone. So here's my volume of a cone. This volume of a cone has an R and it has an H. I don't really want an R and an H if I can help it. And I can tell, again, this R and H and this R and H, those are similar figures. So actually, I can go ahead and, I'm gonna go like this, okay? So I'm gonna go ahead and decide, well, which one do I want? Do I want to keep my R's or do I want to keep my H's? Well, I look at this equation, what am I looking for? I'm looking for H prime. I want to keep my H's. So over here, when I'm solving, so I have R over H equals, I look over here, my big one has two constants, a 10 and a 50. So I know I can relate those. 1 over 5, right? 10 over 50. And then I cross multiply. And then I go, oh, what? H equals 5R. Can't I just plug it into here? Well, if I plug in 5R into here, then I have my volume in terms of R. Do I want it in terms of R? No, I want it in terms of H. So I replace my R with H over 5, right? Because you divide by 5 and you get R equals H over 5. You plug that into the radius. And then from there, I'm going to simplify before I take the derivative. So I multiply, 5 squared is 25 on the bottom, times 3 is 75. H times H is H cubed. Okay, now I can take the derivative a little bit easier. So I take the derivative. So V prime equals, and then my constant, when I take a derivative, I leave it. So this is all a constant. The derivative of H cubed is 3H squared H prime. So if you want, you can just write H prime, that's okay. All right, from there, now that I took my derivative, I can go ahead and plug in. What do I plug into V prime? Negative 12. What do I plug into H? Well, that says H, but is that what I want? No, I want the H prime that's associated with this height, right? So I want this height. So my H is 20, and then I just plug in, I multiply, and then I keep multiplying without a use of a calculator because I don't need a calculator because I can do this on my own, right? 3 over 75 is 1 over 25. Think about $4 in quarters. How many quarters is that? That's 16 quarters. And then go ahead and divide. And then you have negative 3 over 4 pi. Okay, but I want to answer the question. The question is, how fast is the water level falling? How fast is the water level falling? So we are falling at this positive rate. How do I know that my label is feet per minute? Because what is the label for height? This is H prime that I just found. What's the label for H? Well, H is in terms of feet because my volume is feet cubed, so my height must be feet. So that means that my rate is feet per minute. So that's why it's feet per minute. Okay? So give it a try. Ask me questions. You can do it. Okay.